So in arrays and strings, the usual, whenever we get a problem, like, and especially in the interview setting, whenever we get a problem, there's a likelihood of it falling in like a type of a bucket where you know how to approach the problem. And uh, it's not always the case, but it can be case 50-60% of time easily. It can be more than that. So these buckets, basically, I'll just introduce. So these buckets, so you can think of as one of them is sliding window. We have talked about these in our interview programming lab. Well, I'll talk about those algorithms today. It's a sliding window. Then there is a two-pointer approach. So two-pointer is basically, sliding window also uses two pointers, but it's just how they traverse is differs. Then you have another approach of binary search. Binary search can come in places where you might not anticipate, actually. And then there is a fourth one. I don't know, there is no name for it, so I'll have to name it something. So basically, I'll just call it whatever. Let's arrange items by index. There is no name for it, but when I explain, it will become clear what I'm saying. Or probably there is a name and I don't know about it. So let's look at these approaches. So essentially, these are the four things that I want to talk about: sliding window, two-pointer, binary search, and rearrange items by index. Um, all of these, what these algorithms do is they will reduce the time complexity of your code uh, by a whole order. So there is an algorithm, for example, which is working in O of n square. Sliding window will be able to solve it in O of n, or two-pointer will be able to solve it in O of n. Binary search may be able to get it down in log of n. And once again, this rearranging the items may be able to get it down by n. So that's why they become important. So usually when we get asked these problems, it's okay to give an n square solution as a beginning solution. But pretty soon, interviewer may ask about solving it in a faster time, and then you may have to use one of the algorithms. So for example, there is one of the problem that we have discussed in the interview programming lab. Let's begin with that. Right. This is called shortest word distance. At one point, this problem was getting asked a lot. I'm not sure what's the status at the moment, but essentially you have words. You have some array of words. So let's say words can be, let's say, hi, and then something like alpha, and then basically you have moon, and then hi, sorry, say bye, and then another, and then let's say Mars, moon. So suppose you have this list of words and you're asked to find the shortest distance between two words. So your function is of something like of this type. For example, you will like the shortest and it takes basically an array and two words, word one and word two. And essentially what you're looking for is to give the shortest distance that exists in that array between the distance between the two words, word one and word two. Suppose in this case, the two words are hi and bye in this case. So then what is the shortest distance in this case? The shortest distance in this case would be this. This will be the shortest window. The question is, how do we find it? Suppose we get this question, how do we find it? Clearly, there is a brute force way of doing it. The brute force way of doing that would be to run a for loop, pivoting on every single element, and then inside that for loop, run another loop. which goes to the rest of the array and looks for the other word. So I can basically write something like uh, a loop which begins with each item, and that let's say that counter is I, and I'm saying that if that counter meets the word is there is high, then stop there, and then run another loop j on the rest of the array, every item on that array. If you find by anywhere, then compute the distance, this j minus I. That is the answer. So you keep some running total, and let's say the answer is the running total. Then basically answer is j minus I. Then you repeat this exercise again. You move I till you find another high. So for example, you find it here, this location. Then you run the same loop again for j, in which you look for all the buys, and then you can look for j minus I again. And then you can here say that answer equals to the min of whatever the answer you have found till yet, or j minus I in this step. For example, you come here, j minus I is 1, and then answer for j minus I. So if these were the indexes, then basically the j minus I initially was 4 minus 0, which is 4. And then, 3 minus, this was 3, and this was 0. So 3 minus 0, which is, you can say 3. And here it is 4 minus 3, which is 1. So you can saying answer is either minimum of 3 or 1. And then the answer comes out as 1. So that is the shortest window where this exists. The penalty here is that this code is doing unnecessary work. And that unnecessary work comes in the form of that of n square. You have two loops which are going to scan all the items repeatedly. And that repetition causes this n square number of comparisons. And hence the complexity is O of n square. So this is a problem whenever you have this kind of a situation where you have to find a substring which is satisfying some situation. Okay, then you can for a second think about sliding window. Whenever you think that there is a substring that you have to extract which satisfies a condition like this substring, then you can think of a subarray, not just substring, subarray. Then you can think of sliding window. So how does sliding window work? Okay, let's just get rid of this guy, and then I'll talk about sliding window. Okay, so let's talk about sliding window now. This I and high. How does sliding window work is, in a sliding window, what happens is that you create a window on the targets, and then you expand and contract the window whenever, until you have the sufficient condition met, you expand the window. So you have two pointers, I and j, or you can call it left and right. Let's call it left and right. Okay, you expand the window till conditions are not met, and you contract the window as soon as the conditions are met. So what you do is, for example, in this case, the common algorithm, the common way in which sliding window will always work is this, that you begin an I and j, and then you write some kind of a condition, write just one loop and some kind of a condition that you're going to scan all the items inside this array. As soon as, let's say, the words of I meets the first word, W1 and W2. W1 is high and W2 is by. If it meets this condition that this word is equals to that, then at that point, you're gonna keep the left margin of the window there. So suppose I go to the first word. The first word is high. That means I'm going to put my left window here, left margin of the window here. I'm going to anchor it till I find a by. Then the next iteration, suppose this is my iterator. Suppose this is my iterator. I'm going to write it here. X, I, and J. I comes to 0. So initially, you can say that they are -1, -1. You initialize them with -1. Now, when I comes to 0, words of I is equals to high. So I'm going to set the I to 0 and J is still -1. Then I'm going to move the X to position number 1. 1 is alpha, so I don't need to do anything. Then I'm going to move I again to 2, then 3. As soon as I see that the word of 3 is by, I move J to that location. So I is 0 and J is at position number 3. And as soon as I find a J, I compute the window size at that point. So suppose I initialize the window with some kind of an answer, and which is, let's say, 0 to begin with. 0 means that there is no window at them in this. Or you can write whatever min, or you can basically write the max, some max of something, like infinite number, or infinite number of the size, or the size of the array, because we are going to do the min. Then len of words, you can keep it whatever you want. Then at this point, it's time to compare the window. So you'll do J minus I, and J minus I is, give me a second, let's get rid of this guy, and this is 3. J minus I is 3, so answer becomes 3 at that point. Then you repeat the same process again. J was here. Then you repeat the same process again. You move I to some location. You move your X to the next step, which is step number 4. And you encounter the word high. So then I moves directly to this location. And once again, since you found something, you do this comparison again. Compare with the current answer, which is 3, to this minimum of either. And then you get 1. Then you move your X forward, and then situation will never match. But the idea is you don't have to write 2 for loops. You can write just 1 loop. If it matches one condition, then you set your left window. If it matches your right condition, if it matches the other condition, which is W2, then you match the right window there. So your window begins with this, and it keeps expanding till we find the first by. That's the first by. You close this window, and then you compute the length of this window, and then you move forward. As soon as you find this I, this window is destroyed, and this new window is this guy. This is another window. Hence, it is called sliding window. So this is one of the example of sliding window. What I will do is, after the class, I'm going to send out 3 problems on sliding window, which I think we have already solved in the classes as well. So you guys can practice and understand where it might be applicable. This is the shortest word distance. Any questions here?
No.
The approach number 2, that is very common, is the 2-pointer approach. Just give me a second. The approach number 2 is 2-pointer approach. What is 2-pointer approach? Many a times, you will be asked a question. Suppose that, let me ask you a question. For example, you have, this has been asked in the interview programming lab, so some of you might be familiar with it, but we can still discuss. Suppose you have an array which contains ones and zeros. And suppose you have to sort this array. How would you do that? So this problem is basically, you can call it sort colors. So you can call 0 as one color like blue, and one as green. And let's say this gets asked that suppose you have to sort these two colors. So all the zeros are on one side and all the ones are on one side. How would you do that? This question gets asked. The This is a classic problem, and what happens in this case is, the usual temptation is basically to sort. What if I call this the normal sorting functions? If I call the normal sorting functions, then this thing will completely sort itself and you'll get the answer. The drawback of that approach is that, first of all, the time complexity. So a normal sorting algorithm, n log n, would be the time complexity of that code. And the problem with that code is that it does some redundant work, and it does not understand that the nature of this array. That is, it has only two numbers in it, not a whole lot of numbers in it. So with just being two numbers in the array, is there a way to reduce this complexity? Is there a way to actually reduce this complexity? And the answer is yes, you can do that. And we can use a two-pointer approach to do that. In a two-pointer approach, you set up two pointers, as the name is mentioned. And in the sliding window, there were two pointers as well. But in two-pointer approach, pointer number one is here, I. And the pointer number two is here, j. And what you do is basically you just write one loop. You move from here and you move from here. And the approach is that anytime you find something that is not in its place, for example, you found a 1, then you hinge there. You don't do anything until you find a 0 there. And then as soon as you find 0, you swap. And then you move one step here. So for example, in this case, what will happen is, in the step 1, you will find that 1 and 0 are found. So you swap. So 0 is sent here and 1 is sent here. So this will essentially become 0 and this will become 1. Let's just rub this thing. This guy and this guy, and let's just make this 1 and 0 modified array. And then I moves to this location. Now this is I and this is j. Now this I is 0. Sorry, did I do a mistake? Sorry, my mistake, my bad. This was supposed to be 0 and this was supposed to be 1. 0 and 1. Now in this situation, our left pointer, if you find a 0, it's happy. There's nothing to be done. So it keeps moving forward till it finds something which is not 0. Then it stops there. So this is also 1. This will keep moving till it finds something which it doesn't like. In this case is 0. And as soon as they swap. So this becomes 0 and this becomes 1. And once again, they keep moving forward. And they move forward till they meet, till the I equals to j. Or you can write I is greater than j, whatever condition. So you write one loop to say until I is smaller, until I is greater than equals to j, you repeat these steps. So it's one loop, you move from front and back, and you're able to sort this information. Clearly, the time complexity in this case would be linear time complexity. because we are just doing one pass on the array and we're swapping the numbers there. So this approach is actually very effective in solving many problems. There is a famous problem which is called um, Dutch flag problem. So in the Dutch flag problem, essentially is that you have three colors and you have to sort them in one place. So suppose the three colors are denoted by numbers 0, 1, and 2. So suppose you have 0, 2, 1, 0, 0, 2, 2, 1, 0, 2, something like this. You have to sort all these numbers in. You have to sort all of these numbers in a way that the colors are sorted. So zeros are together, then ones, and then twos. So how do we do that? Once again, we can sort the whole array. If we just do a plain sorting in this case, then that would be n log n. But given we just have three numbers here, can we do better? Is the question. The answer is yes, we can do better. What we do is, this most simplest approach we can do is we can run the same code that we did. And in the previous logic, we'll just change this a bit and say that there is I that begins here. And then there is J that begins here. Last time, J was happy whenever the condition matching above was 1. But now we say either it's 1 or 2. So what we do is we first sort 0 with the rest of the numbers, and then we sort the 1 and 2, the rest of the 2. So for example, I and J are here. They are in correct position because 0 is supposed to be on the left and this is supposed to be on the right. Now suppose you encounter I comes here and J moves here. Now you notice that there's a problem. So essentially you sort it out. So what you do is you move 2 here and 0 here and 2 here. Then I comes here and J comes here. So I is unhappy right now because there's 1 here. I want to swap it. So, but J is okay. So J will continue moving in this direction until J reaches this point. Then J is unhappy now. So you swap 0 with 1. So what happens is in this array becomes the 1 comes here and 0 comes here. So now you see that the array is sorted at least in two different groups. I have considered 1 and 2 to be the same group, and I've considered 0 to be the one group. So in this case, we have done n comparisons already. And we have sorted the array into two groups. Now, with the previous computed information, our I was here. We can do the similar operation again by using the 2 pointers in this situation, where we take I, like one of the color is 1 and color 2 is blue. So color 1 is 1 and color 2 is 2. So now we're just going to swap 1 and 2. Similarly, this and this, and we ignore this guy and we'll sort it. So first, in the first round, we did some n comparisons. In the second round, we are going to do some m comparisons where m is less than n, always, because m is size is smaller than n. Essentially, it will be at the max 2n comparisons, which is equals to O of n complexity. Any questions? All right. I'll give you another very simple example of this. Things get asked, for example, suppose you're given a string. Okay. Let me think of a good string. Actually, just take the string. Suppose this string, universe. Suppose there is a question here. Um, let's just take some bigger string. Let's just take a string. Let's say I am. Let's just keep all small. Let's just do this that much. So I just keep a bigger string there. Suppose you're asked in this question to swap all the vowels. So from the beginning to the end, if you find a vowel, then you swap it. Otherwise, you don't do anything. So in this case, A and I get swapped. And then this A gets swapped with the next vowel here, which is this guy. So this same. And then I get swapped with U. So if you have to do this problem, for example, you have to swap only the vowels in this string. Then once again, the similar approach works. You begin with here and you begin with here. You keep moving till you find a vowel here, and you keep moving backwards till you find a vowel here. The moment you find vowels in both the position, you swap. Essentially, that's the only logic here. So this problem, if asked, can look tricky, but it's not tricky in that way. Some of the other problems in this category are the maximum water area. So you're given, for example, an array, and each item on this array represents, let's say the array is, actually let me draw it again. So each array has a like some items in it, some value on it. So suppose this is a 5, 4, 1, 2, 9, 0, 13. So given this array, and let's assume that each item on that particular index represents the height at that particular place, then if you draw it, then essentially what is the maximum amount of area formed by any two regions? So for example, this is, if you take 1 and 2 index, then if 1 or 2 items, then this is the area formed. So the problem is, what is the maximum area that can be formed? So the test case I have written is actually not that complicated. So you can visually see what the maximum area is here. But there can be complicated cases. Actually, this one can be complicated too. I'm sorry. This might very well be complicated itself. So what is the maximum area that can be formed? Suppose these are the indexes: 0, 1, 2, 3, 4, 5, 6, 7. And you have to find the maximum area here. In that case, for example, what you can do is you can write two for loops. So one goes with I from 0 to whatever n, and then j, which goes from I to n. So for 0, we can compute all its area with all of the indexes. Then with 1, we can compare all of the area with all of the indexes, and we can do that. And whatever is the maximum, we can return that answer. So for example, between this and this, the maximum, the area here is this. So this is, length is 1 and the height is 4. So that will be 4 units. If we continue in that way, then essentially we come to a point, then basically we'll be able to find the maximum area by n squared comparisons. But you can solve this problem again using two pointer by going one from here and one from here. I will send this problem in the follow-up, and then you guys can take a look at this problem. Try to see if you can solve it. It's an interesting problem. The third approach is binary search. Binary search, for example, suppose you want to find a number in an array. right? It comes from that particular, uh, the search word comes from that fact that we are looking for something. Suppose you want to find a number in an array, which is some random array: 100, 90, 50, 75, 29, 30. 101. So it's not unsorted, essentially. If it's unsorted and if we want to find something, then the problem here is that we have to look each element from left to right. We have to compare each element from left to right. Otherwise, we will not be able to find that element. So that's linear search. Linear search is O of n. However, if the array is sorted, suppose the previous array was something like 29, 30, and then whatever, 50, 75, 90, 100, and 101. If it's sorted, and let's say if I ask you to find number 90, then the question is, do we really need to start from the beginning and look for every element? This is analogous to, once again, finding, let's say, a page number in a book. If I ask you to find a page number, let's say in a book which is 140, find page number 140, then you don't go from page number 1 and look for all the way to 140. You know that all the numbers pages are in sorted order, so you can open a random place by approximation and then move back and forth from there. That's the idea of binary search. So essentially, if I ask you, the usual binary search algorithm will always run like this: that if I want to find something, I will set two pivots. One pivot is called left and other pivot is called right. And then we will set a middle which is equals to left plus right by 2. So let's say in this case it is 75. Then what I do is I compare. This is a common step in binary search. This will happen. Then I compare my middle element with the key 90. So my middle element is 75 and the key is 90. This array is in sorted order. That means 90 cannot lie in this region. Hence, I only need to consider this whole region. So at the very first step, I have reduced let's say the array was n, then I've reduced the array to n by 2 in the very first step. The one step that I missed was the first thing that you do is you compare the middle with the 90. And if you find that it is 90, then you return it. You found the answer. But if you don't find, then one of the halves get completely reduced. So once this is being done, then you move your left to the middle plus 1. So your left comes in this location. And you compute the middle again. So which is left plus right by 2. So middle comes in this location. Then you compare 90 with the middle again. Are they same? They are not. But my middle is bigger than the 90. That means this space does not contain the answer. So I move my right to middle minus 1. Right comes here. And the left plus right by 2 is also this position middle. And then the middle is equals to middle and you return the answer. You have found the answer. Or vice versa, if you don't find the answer, suppose this was something else, suppose this was 89, then the middle will not be equals to that. And in the next position, if this is not the case, then either the left will move here and the right will move here. And that will break the condition because we initialize this with saying while left is less than right. Till then only learn the loop. And if you don't find the answer in this, until this condition is, if this condition meets and we have not found the answer, then the array does not contain our answer. So that's essentially the binary search. What happens is each space, at each step, there was an array of size n. You move it to array of size n by 2. Then the next step, array becomes n by 4. So essentially, this series is what log n is. So you just essentially going to do log n number of comparisons in this case. we did some recurrence relationships in past, you can go to that and verify that. That's binary search. Binary search is actually very helpful. It There are some classic problems, once again I'm going to send you, that you can check, which is called mountain or finding the minima and all that. It is applicable in actually other situations as well. Suppose take a general array. Suppose there is an array like 5, 10, 15, and then 6, 9, 1, 5. Suppose these values, this is an unsorted array at the moment. And this problem is called, let's say, find peak. So the question statement is something like, each number here represents a value, which represents the height at that particular location. So suppose this is 5, this is 10, this is 15, this is 6, this is 9, then this is 1, and then this is 5 again. So essentially, if you look at it, then this becomes a kind of a mountain in that way with local hills. So your task is to find if there is a peak in this array, and if there is a peak, then find any peak, return any peak in that array. You can consider this to be minus infinity. A peak is defined as any index I, for example, this, any index I where AI is greater than AI plus 1, and it's also greater than A of I minus 1. So this element is not a peak because this does not match this condition. We are going towards the top. This is a peak. This is not a peak. This is a peak. So this is a peak. This is a peak. This is a peak because the left is all the left items are small, and the right item is minus infinity. This is not a peak because this item is bigger than the previous item. 10 is bigger than 5. So this array is even unsorted, and in this case we are asked to find a peak. Then one solution can be to run a loop from here to here for each I. For I from 0 to whatever this n, and for each I check this condition if this condition is true. If this condition is true, then return I. That can be one answer. But what would be the time complexity in that case? The time complexity in this case would be linear because you're comparing each item. Can you find in a shorter time? The answer is yes, you can find in a shorter time. How can you do that? You run the binary search. So in the binary search, you begin at a very random point, any random point. The condition remains same. You set up two elements, left and right. And you write a loop while left is less than equal to right. While left is less than right. You run this loop. And you're going to find the peak in this way. For example, you compute the middle. So let's say the middle comes out to be this guy, 6. Then you check middle with your neighborhood. So how is the m plus 1 and m minus 1 element? If this is a peak, then return it. But in this case, it's not a peak. You will notice that that this element is smaller than both the element. So in this case, we are either coming from a peak or we are going to a peak. That is certainly clear. We are either coming down from a peak or we're going from a peak. So this is actually a kind of a bad example because I chose something in the middle, which is actually a complete valley. But if it was something else, then it would be interesting. But that's fine. This is going to revolve. This is going to go in a good way. So suppose we can choose in any direction we want. So let's assume that we say that we're coming from a peak. So peak is somewhere here. Remember, we have to return any peak. So I'm just going to discard all of this, move the right to this location, compute the middle, which comes here. Now, when I look at middle, I will notice that uh, the right element is bigger and the left element is smaller. That means we are going towards a peak. That means we can move the left here and middle here. So once we move left here, that means middle becomes that. Now when we compare middle to the next elements, this and this, we find the peak. So if there is a peak, if there is a peak that exists, then we'll find it in log n number of steps, because we are once again reducing the search space. And once again, I'm going to send you this problem, so you will be able to solve it yourself. But it's an interesting problem, nevertheless. Another interesting area where binary search is good, applicable. They generally fall in the category of binary search whenever we are reducing the search space by half, or we are reducing the number of iterations. Suppose there is a problem in which you are asked to compute x to the power n not using the power function. You have to write a code to compute x to the power n without using the power function. Then how do we do that? So you have to write a function which is called power function, which takes 2 arguments and gives x to the power n back. Now, the normal thing that comes to head is that just to write a loop, like basically for n in whatever 1 to for x, sorry, my mistake. Let's say for I in 1 to n, basically whatever you have, answer equals to 1, then answer multiplied equals to x. Or essentially, let's just even rub this. Essentially what I'm trying to say is, you might think of writing a loop that multiplies x by itself n number of times. That will give x to the power n. So essentially you can do this with n multiplications of x, and you can return the answer. And given you're going to do n multiplication, this O of n time complexity. The question is, can we do better? And of course, the answer is yes. How do we do better? We understand a simple fact about what we have just done. We have done a lot of repeated work. Suppose the question is to compute 2 to the power 8. Assume this. Then we can write a code which is going to multiply 2, multiplied by 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 2. So essentially you have done what? How many operations? 8 multiplications. Question is, do we need all these 8 multiplication? In the very first loop, we'll multiply 2 multiplied by 2, and we'll know that it is 4. Then do we need to do the rest of the 2 multiplied by 2s anywhere? We already know the answer. We already know the answer now. So now the next answer becomes 4. We know that this is 4. Then we multiplied 4 and 4, which is 16. So we know this answer as well. And then we can multiply 16 by 16, which gives 256. So we don't need to do 8 multiplication. For 8, we did 1 multiplication, then 2 multiplication, and then 3 multiplication. which happens to be the log of 8 is 3. So this is log of n, number of multiplications you can find the answer. So it finds itself in many different ways. Now, the interesting part becomes, what if this was 2 to the power 9? What if there is an extra 2 somewhere here? Then also you can solve the same problem. You just have to do one more multiplication in the end. And that way you will get the answer. It still be log n, because there will be log n plus one operation. This is essentially log n. Any questions? And the last category I'll briefly talk about. This question gets asked. For example, suppose you have an array of size n. Usually, the trick to this situation is that you will be given an array of size n, which will only contains items from 1 to n. That will happen. One second. The trick to this particular question is, whenever you are given this situation, when the array is size n and you contain numbers from 1 to n. So suppose the array is size 5. 1, 2, 3, 4, 5. And the numbers contain, sorry, what did I do? 4 and 5. And the numbers contained here would be from 1 to 5 as well. Okay, so suppose this is whatever, 5, 4, 3, 1, 2, something like this. Or they can be duplicates or however. In this situation, this trick is applicable. You will be asked, for example, suppose that you are given one such array and one of the number is duplicate. One of the number is duplicate, suppose this. Then find the duplicate number in that case. So the problem statement will be, given a size of array n, which contains numbers from 1 to n, one number has been duplicated. Can you find the duplicate number? Or one number is missing. Can you find the missing number in that case? The question is, how would you do this problem? The usual approach that comes to mind is basically to create a set of numbers. So what you do is you go from left to right. And as you encounter the items, you put them in the set. So suppose you begin this and this is your set. First we go to 5. So we put 5. Then we go to the next item and we check, is this item already present in the set? No. Then insert it in the set. Then we go to the next item. Is this item already present in the set? No. Let's insert it. Then go to the next item. Is this item already present in the set? Yes. That means this is the answer. 3 is the duplicate. So this is the usual answer that you will propose. But the next question that's going to come is, can you do it in place? That is, can you not use this guy? Because this is on of time. So this basically, the previous algorithm had on time and O of n space, because we created this guy here. So can we do it in less than, in like O1 of space with on time? So that's the follow-up question. So you come to that. Yes, the answer is, of course, is you can do that. And the usual trick to this problem, is rearranging items in the array itself. So what you do is you start putting items in their correct places. So I go to the first place and I say this is 5. The 5 should go to the index number 5. So I put 5 here. That means this 2 needs to go in a place where the 2 is. The only thing that we need to check is that item already present on that index or not. So when we moved 5 here, we notice that it's 2 there, so we don't care. So now we're going to move the 2 to this guy. 4 is not 2, so this is okay. I'm going to place 2 here. Now let's move 4 to its location. So we move 4 to 3. 3 is not equals to 4, so I'm happy with that. So then we come to 3 and we move 3 to this location. And we notice that on 3, there's 3 already present. Hence, the 3 is a duplicate. So this is a coincidence that 3 was present here. Even if the 3 was here, then eventually you will end up in a situation where you will reach an index where that particular item would already be present. If an item is more than 2 times, then that item will reach that index twice. And as soon as you reach that situation, you know that it's a duplicate, and hence you can return that answer. So if there is a name for algorithm if you guys know, you can write it. But I mean, this kind of problem comes, and you can solve it this way. And it's been a couple of times I've seen this problem get asked, and through experience that when you have to solve it using the shuffling of elements. Any question here?